Number 14 off the 1996 Physics GRE practice exam. 14. Two identical 1 kilogram blocks of copper metal, one initially at a temperature T1 equals 0 degrees Celsius, and the other initially at a temperature T2 equals 100 degrees Celsius, are enclosed in a perfectly insulating container. The two blocks are initially separated. When the blocks are placed in contact, they come to equilibrium at a final temperature Tf. The amount of heat exchanged between the two blocks in this process is equal to which of the following? Specific heat of copper metal is equal to 0.1 kilocalories per kilogram degree Kelvin. Quick look at the answers. They all have the same units. They are just numerical values of energy there. We're going to have to do a calculation and select which of those is the correct one. It's a very straightforward problem. As it turns out, you can solve it with just one equation that you have to remember, and that is the equation for heat and specific heat. Change in heat energy is equal to the specific heat times the mass, which is exchanging the heat, times the change in temperature. That's really the only equation you need to solve this problem. Let's diagram it out real quickly just so we know what's happening. They tell us we have two of these blocks, one at 0 degrees and one at 100 degrees. They're initially separate, and then they are pushed together and put inside an insulating container so that no heat goes anywhere else, but heat is exchanged between the two of them. And that's key. We need to know that this is at equilibrium. So when these are pushed together, we don't know how much time elapses, but we do know that both of these have reached an equilibrium there at some T sub F, some final temperature. So they've changed. This one has increased by some amount, T sub S, and this one has decreased. Intuitively, you should realize that the hotter one is going to get cooler and the cooler one is going to get hotter. So heat is going to move in this direction once they are pushed together. Of course, it's going to move from the, make an arrow there, from the hotter body to the cooler body. And then it's asking what is the amount of heat, or heat energy, if you will, exchanged between the two blocks. So another way of saying that, and this is, I guess, important to this problem, is that you need to, another way to say this is we could say how much heat is lost by the 100-degree block, or how much heat is gained by the 0-degree block. That is equivalent to the amount exchanged between the two blocks. Any of those three ways of saying it, heat exchanged, amount lost by the hotter one, amount gained by the cooler one, those are all the same quantity. So that's what we're trying to get here. Again, you can just, if you're ready to go and it's intuitively obvious to you what's going on in this problem, you can solve it almost in your head. You can solve it in your head, I bet, by just using this equation. To be a little bit clear about it, though, I'd like to do one extra step. How do we know what the final temperature is? Intuitively, if you know, that's great. But as I've just said, you can figure out what this final temperature is by comparing the two things that I've just said. We know that the amount of heat gained is going to be equivalent to the amount of heat lost. And so we can equate two of these. We can say, okay, this, I'll start with the 0-degree block and look at the amount of heat gained. So this is, what I'm doing is this is going to be temperature final minus temperature initial. And I'm going to put these equal to each other. So on the left-hand side, I'll do the 0-degree block. We have its final temperature minus its initial temperature, which is 0. And I'm going to equate that to the 100-degree block. And that's final temperature is T sub F. Its initial temperature is 100. Okay, so as you see, these two sides, these two quantities are going to cancel. They are identical, and this is 0, so you just get T sub F equals T sub f minus 100. You do the algebra, you get a negative 2 T sub f equals negative 100. You multiply by the negative sign, and you get T sub f equals 100 over 2, which is 50 degrees Celsius. And hopefully that's obvious to you, that intuitively it would be halfway between. But for those of you that were wondering, and it won't always be that case, of course. It won't always be the case. If the masses were different, for example, if they were not both 1 kilogram, it would not be the case. So that's why I did this, just for that sake. But it's 50 degrees, and so that's going to be the change in temperature, because you went from 100 to 50 or 0 to 50. That's going to be our change of temperature. So let's do our final calculation. The change in heat energy is going to be equal to this, which is 0.1. I'm going to leave the units off and talk about the units as I go. We both know it's a 1. We know both the masses are 1 kilogram mass, and then the change in temperature is going to be 50. And the units are important to this problem in that there's a little bit of a trick here. We have calculated this as 50 degrees Celsius, and the constants they're giving us for the specific heat is in degrees Kelvin. So is there a problem there? Yes and no. Yes and no. They're different units, and you should have noticed that and been aware of that, because that could be a problem. In this case, we don't have to do a darn thing about it, because the difference in a scale, whether it's in Celsius or Kelvin, is going to be identical. If you recall, to convert from Celsius to Kelvin, you just add the constant. So 0 degrees Celsius is 273.15 degrees Kelvin. And then the 0 point for Kelvin is at the absolute 0, right? So you're just adding that constant. So a difference of temperatures is going to be identical whether it's in Celsius or Kelvin. And prove that to yourself. Notice that the 273.15, it's just going to cancel out when you take a difference that is not the same. Incidentally, if you have something like degrees Fahrenheit, or you have another, I guess those are the main ones, but degrees Fahrenheit is not like that, even though you do have a constant that you're adding on there. The degrees, 1 degree Celsius is not the same as 1 degree Fahrenheit. But is so in these two. So as it turns out, this is also 50 degrees Kelvin. I'm sorry I'm being long-winded about it, but these units are just fine. It's just a straight multiplication here. 0.1 times 50 gives me a 5, and D is 5 kilocalories, and that's the answer that we're looking for.